Afternoon, all. Hope I am audible. The from okay, so still now we were looking into the concepts of our basic digital designs. Okay, so from this onwards, we will be looking into the hardware description languages and uh, we are moving into the Verilog coding stuff. So first we will try to look into the history of the how this hardware description language has been evolved since now. Okay, so whatever you try to learn, you have to get an idea about the history, how, why, and all such kind of things. Okay, okay. Yes, once again, good afternoon, all. So, we will be moving into the session. Okay. So, when we talk about the history, how of the hardware description language. So, what is that hardware description language? How it is getting evolved? Okay. So, as the digital system became more complex, the designing the circuits using only schematics and manual gate level methodologies become impractical. So we were been trying to develop a complex machines, and since the we want to develop the more sophisticated digital systems, designing the circuits by using only the schematic and by using the manual gate level methodologies, it was it was something, it was impractical. Okay, when we try to have uh, designing the circuits which is having a complex thing. So there evolved the hardware description language. You see, for the automation of the microcontroller, we will be writing in zeros and ones so that the controller will do it. We are not able to good with the machine language, so we went and used C language, C plus plus, so some other languages, so human can understand it, and some software thing we went and compiled and we are converted into assembly, then into the zeros and ones, that is machine language binaries, and we are able to flash it. Okay, that is another thing. Now, to develop a hardware circuit, please try to understand what we are talking, that is fully software. Now, to develop a hardware circuit, they developed a language, we are writing a software. So using that software, where we are able to synthesize the hardwares. Okay, that is what the difference. So hardware description languages and structured design methodologies evolved to manage complexity and improve productivity and ensure correctness. So to have a proper design methodologies and to manage the complexities and to improve the productivity. So this hardware description language, it was simply it started evolving for the application specific integrated circuit, field programmable gate array, system on chip, and for communication ICs, AI accelerated, embedded digital hardwares. These all are complex circuits, and we need a structured design methodologies. Okay, so those are the things which you guys want to. So that is why this hardware description language, it has been slowly it went and evolved. Okay, so first let us see the evolution in the digital design. So at what period the hardware description language has been entered into the digital design. Okay, so when this hardware description language entered inside the digital design. Okay, so evolution of in the earlier eras, okay, long back, so they were trying to make the circuits, design it in the manually, they were trying to design the circuits manually using logic gate diagrams, truth tables, Karnaugh map, and transistor level schematics. They were trying to design the circuits in a manual way. So what is its characteristics? We are able to draw only a simple circuits only, and only a small number of transistors, not millions and billions of transistors. They were able to do it with only small number of transistor counts, okay, and highly error prone, okay, and poor scalability. So when we try to use design manually using, these are the things which we are facing it. So because of this, they were able to produce only counters, adders, and small controllers. But the problem is, in the modern chip, it contains millions and billions of transistors. So manual design is impossible. How you are going to design a circuit which is having millions through your manual way? You go and keep the manually, you have to go and add the transistors, gates, and all sorts of such kind of things of millions and billions of transistors. Means, you think, okay, how awkward it will be, because nowadays the modern chips is having millions or billions of transistors. So you think of, if we try to do it with manual way, we go and design the circuit and put it, you take the time, and how it will how hard it is, okay. So now there is a need for some language where automatically the circuits and everything, design circuits where we can go and do it. So when the challenges were growing complexity, that is, we have a huge transistor count and we need some verification. So from something, we have designed the circuit and we want to verify that circuit. How? And it also became a difficulty, okay. And then once we designed the things, the we want to reuse it, but we are not able to reuse it when we are trying to design it in a manual way. So that is also another problem. Then documentation issues, whatever the design, see, for making the design itself, it is a lot of time. Then again we want to spend time on the document and all those things, it is, and poor scalability. And suppose if we want to do any modifications, then it is also of great difficulties. And there is some, whenever we try to get a simulation, it is of only with limitations. We cannot go on to fully, we are not able to verify the things, okay. So these are the challenges we faced without the HDL. So they introduced HDL, so it will describe the hardware behavior. The hardware description language, it will describe the hardware behavior and simulate the design before fabrication. Before we are going into the fabrication stage, before we move into the fabrication stage itself, the hardware description language will help us to simulate the behavior and all those things. And we can improve the reuse also, the design, small designs where we can go and reuse it, okay. And automating the synthesis, okay. And then it is of reducing the error, and we can speed up the development. So these are the challenge we face when we try to do manually. Because of these challenges, they introduced the hardware description language, and it went and solved many of the things. And still now also it is solving many things, okay. So that is where the need of hardware description language has arose. So now we will try to understand what is this HDL. It is hardware description language. So we have seen a software languages, likewise they have one systematic way, a systematic language where it will describe about the hardware. That is where hardware description language. So used to describe digital hardware at multiple abstraction levels. Okay, you please try to understand this abstraction. This is very much important. Okay, so abstraction means we have something, okay, in that something in an, we are trying to abstract the real thing. There is some real thing, we are trying to abstract it. That is where the abstraction comes over there. Okay, so when we come to the real hardware design, there are multiple abstraction levels. Okay, so there will be some abstraction levels, then it is moving into the real thing. Okay, so that is what this abstraction levels takes. So unlike software languages, HDL describes us. You think that this software languages, this is different and this is different. So here the software languages will go in a sequential way, but this hardware description language, it is parallel hardware behavior, parallel. That is what you have to understand. And it is timing relationships, signal interactions, concurrency. That is where the parallel and all those things, concurrently it go and do the things. So that is why it is totally a different from the software languages. Okay, like C, C++, Java, Python, those are the software languages. And HDL describes the hardware behavior in a parallel way, and its timing relationships, signal interactions, and concurrencies. All the things are described by the hardware description language itself. Okay, so for example, Verilog, VHDL, and system Verilogs are some hardware description languages. So these are the things, and we will try to learn this Verilog language. Okay, so under the 1960s to 1970s, digital design mostly in schematic based. So now we will try to see with the era, and we will try to understand. Okay, so there, during that time, the hardware description language is nothing but they will do a transistor diagrams and gate level designs and manual simulation. So the industry limitation is it is slow and it is expensive. Okay, so during 1960s and 70s, they were able to draw the schematic based. So that means they will draw the transistor diagrams and some gate level designs and some manual simulations. They will do some manual simulations, and then industry limitations, slow, and it was expensive. Okay, then in 1980s, only the real hardware thing has been emergencies. I mean, it has been came into effect. They have been developed. So the first language is VHDL. The first language is VHDL, and its full form is very high speed integrated circuit hardware description language. Very high speed integrated circuit hardware description language, that is VHDL. It was developed by US Department of Defense by VHSIC program. The purpose of that is to standardize digital hardware description. They need some, to describe the hardware, they need some standardized thing. So it is strongly typed, verbose, and highly structured. Then they went into the IEEE standard, and mainly they used for aerospace, defense, and for application specific integrated chips. So for that purpose, they went and used this VHDL. Okay. Then the Verilog developed. It was developed by Gateway Design Automation. That company went and developed it. So the purpose is it want to be a simpler hardware description language for the practical design. So the syntax is similar like a C-like syntax, and easily we can go and learn, and a compact coding style, and later they standardized it to 1364, and now widely it is adopted in industries. Okay, So this is where the in 1980s these VHDL and Verilog entered. Okay, in 1990s synthesize revolution come. Sir, what is synthesize and everything? No, see, till that they were able to give only in the schematic and simulation such kind of things. Synthesize means that schematic level you have to synthesize to hardware level. So hardware schematic, see, by seeing the schematic, that is different. When you are able to synthesize it means that is converting that into an hardware level mapping. Okay, so the major shift in 1990s, how it happened is the hardware description language becomes synthesizable. Before that, where we can go and see only simulation, now we can check the simulation using the language itself. You can design for the hardware. You are able to realize it. You are able to synthesize it. That is where. Okay. So after that, HDL, they used logic synthesizers, and that will be easily, you can convert that into an hardware. So because of this, what happened? No, massive productivity improvement happened. Yes, during the 1990s and all, lot of things has been done. Okay. So the tools like Synopsys Design Compiler, Cadence, and Mentor Graphics, they were able to have an synthesizable hardware description language. They are synthesizable hardware description languages. Okay. In 2000, it is something advanced verification era. Okay. So that is where. So we have 1960s to 70s. Okay. 80s, 90s, and then 2000. Okay. In 90s, synthesizable came. Okay. So in 2000s, it is advanced verification era. So growing complexity required better verification, because the human need and everything, they were trying to make it in an automated and trying to bring it in the chip level and everything. They were trying to make it compact and all such kind of things. Okay. So they need a better verification methodologies. So technology like system verilog, assertions, constrained random verification, functional coverages, universal verification methodologies, these kind of technologies has been involved. So the focus has been shifted from design plus verification. Okay, before moving into the fabrication, they will design and they will verify. Those things are happened. That era is 2000. So they went and verified with the advanced techniques, advanced technologies. Okay. And from 2000 till at present, this is the modern design trend. Now you try to understand. Okay, this is the modern. So the, see, previously when we in the before 2010 and all, we will go and buy 8051 microcontroller. We will ask microcontroller and we will buy. Nowadays it becomes system on chip. System on chip. So that it is changed. Okay. And then something field programmable gate array acceleration has been involved, and our open source RISC-V. Okay, they went and invented the RISC-V architecture, and they have been, it is open sourced. So because of this, lot of things. And then AI chips also started arriving. AI. And then because of these all things, previously when we try to simulate any hardware design, we want to have a proprietary softwares. But nowadays there are many open sources. In the online itself, it started moving into it. And the other beauty is this hardware software co-design. So hardware people and then software, we are trying to improve through the help of software by the hardware, and by the hardware we are trying to improve the softwares. So so we will try to design the chip by having hardware and software co-designs. Okay, so hardware will take care of something and software, you see, maybe the exact gate level will be in the hardware, the bus and all kind of such things will be in the software side. So you will be, so there's a hardware and software co-designed, it happened. Okay, something like protocols, UART, SPI, such things comes. So to do that, lot of tools has been come. So system Verilog, Chisel, BlueSpec, MyHDL, open source RTL flows. So these are the tools which has been evolved in the modern design trends. Okay. So hope you get the under. I try to capture the futures of VHDL and Verilog and compared. So its origin is data on demand. So something data on the demand, because of that it origin. It is origin it with the gateway design. Okay, syntax it is full verbose, but it is going to be compact. This Verilog is compact. It is harder to learn compared to Verilog, but Verilog is easier to learn. Okay, so it is strongly typed language. It is somewhat a weaker typed language. And then aerospace and ASIC they entered used. It is main for FPGA and such kind of things. Okay, so it is explicit and it is concise towards its readability. Okay, so now we try to understand the HDL. Okay, and then I already told that HDL supports many abstraction levels. Okay, there are many abstraction levels. Then only it goes to its original stuff. Okay, so HDL supports multiple abstraction levels. Okay, so what is that? Behavioral modeling. So the levels of hardware modeling. So how you can model your hardware. So this is one kind called behavioral modeling. So it will tell, this model tells that what the system does. That's it. It gives the behavior. Okay. So the teacher's behavior is to teach something like that kind of things. It goes and gives that. For example, counter increments every clock. That is what its behavior. So with this modeling, they will able to have a high abstraction and easier modeling and fast simulation. So this is what it is. We will see this one by one later future classes, but try to get the terminologies. What is behavior modeling? Okay. Next, there was something called an data flow modeling. Okay, so this data flow, how the data going to be flow, that will be described. So it gives the signal, it describes the signal relationships. For example, the Boolean equations. Okay, that is where the data flow modeling. Next, gate level modeling. Okay, so what are the gates it is going to use? So I am talking about the abstraction levels of the VHDL. I mean HDL, hardware description language. Okay. Next, switch or transistor level, it goes into the mass transistor modeling. Okay. So it gives the detailed circuit simulation. So these are the modelings and they have their own abstractions. That is what HDL is capable of having multi-level abstractions. Those abstractions we were trying to peel it. Behavior modeling and then data flow, gate level, shift, switch and transistor level, such kind of things. Okay. So in the design methodologies is structured approach for converting specification into hardware. Okay, the meaning of design methodology is given in this slide. Moving a structured approach without anything. See, first if you go and build the ceiling, then you go and build the basement of your house, how it looks. So we want to go in a structured way. Okay, that is called the design methodologies. Okay, so the goals of this design is to reduce the complexity, improve reuse, enhance verification, shorten design cycle, and improve maintainability. Okay, no need to remember on all those things. I am giving you an idea why. At the end of the session, I will try to write one program. Okay, I will type and write one program, and I will tell how to compile the system Verilog. Okay, and there comes one design. Okay, design methodologies. The goal is the complexity want to reduce, we want to reuse that, it want to enhance the verification, and the time take to design and hardware, it want to get reduced, that cycle want to get reduced, and the maintainability also want to get improved. Okay, so they choose something called bottom up design and top down design. So what is that bottom up design? It starts from, so actually there is a dedicated session for bottom up design and top down design, but here let me give you some introduction about that. Okay, so the it starts from small module. Bottom means from the small modules you combine, it become a big modules. Those big modules will combine and form a structure. Okay, so that is the idea. So start from small modules, build larger system progressively. So gate, adders, ALU, processor, so that we can go and reuse it. So reusable modules and easier. So the verification, how we are going to test it, the unit test is becoming easier. Okay, so the architecture may be inefficient because we are going from low to high. So there is a chance of inefficient architecture. Okay, in the top down, from the top, so it starts from the specification. So we will go and get what is the specification of the system we need, and then from the specification we will try to build into smaller modules, and these modules are built into smaller modules. So something like that. Okay, example, data path, ALU, register file, control logic. So here we have a clear architecture and scalable and manageable complexity. This is where the preferred modern approach from top to down steps. Okay, this is where the thing. We will see these things a dedicated session. Then there is an hierarchical design also. They have the hierarchical design. Okay, so I told nowadays the system on chip, so they will have one hierarchy. This is the chip. In this hierarchy, inside you need the CPU, microcontroller, UART, SPI, and timer. So in the modern SOCs, you will have the core, that is the CPU, and that is connected to the buses, and with this memory, controller, peripherals, UART, SPI, and timer, and this everything is built up inside a chip. So something like in an hierarchical design. So the modularity, reuse, pickupping, and parallel team development can be go on these things. Okay, that is what the thing. So what is this modular design? So each functional block designed independently. Okay, so you can go and design this UART independently, SPI independently, timer independently, memory control independently, CPU independently. That is where the modular design comes. So UART. Okay, so for the you see, that is one example. The other example, inside the UART, you can generate the board generator by some team, and a TX finite state machine transmission. For that finite state machine, someone can generate and something can generate, and for the shift register, some other people can generate. Okay, so we can go and reuse it. Okay, so it is for UART1, UART2, you can go and reuse the things, and maintainability and easier verifications, those things, it will be easy. So this can be designed independently, this independently, and we can club it together to become one UART. That is what I'm trying to tell. And if you want to do it for another system, you can reuse it and you can maintain it easily because of only one, because it is in the blocks, in a small blocks, you can go and reuse it, and it is easier for verifications. Okay, so these all are some advantages when we try to use this modular design. Now, RTL design methodologies, this is the most common modern methodologies we were trying to use it. Okay, the flow is architecture level, we will tell this is what I need. The architecture, the CPU only for the load and store, it want to come here. All the things it want to work over here, only for storing it will come to the memory. All the operations want to do this. So something in an architecture level they will specify, and they will do RTL coding simulation, then they will convert that into synthesis and static timing analysis, then go for the physical design. This is where the flow for the RTL design methodologies. Okay, so we will be having a synthesizable hardware description language and synchronous design and timing aware. So everything is taken care by this RTL design methodology. Okay, now there is another thing called ASIC design methodology. It is focused, okay, to a specific hardware. Okay, so the people will go only for these designs. The company will go if they need more product, if they going to develop more product, we are going to develop a huge number of amounts, that only they will go for it. It is high cost. It is totally when it's going to develop because it is for only a specific program. I mean specific design, application specific. It is for only one application. It is not for general purpose or something like that. So they have their architecture and RTL verification, synthesis, and the design flow test, floor planning, placement, and then CTC, CTS, routing, sign off, and tape out. These all are the flow of this ASIC design methodologies. So it emphasis on the power, timing, and the manufacturability. Okay, so the people it costs more. That is what the thing, because it is for only for a specific applications. Okay, next FPGA, where we will go and write, design the hardware. In the hardware itself, we will design an hardware and we will go and test it. That is where the FPGA design methodologies. So there are also RTL simulation, synthesis, implementation, and by the bit stream we will put it in the board and we will try to check it. Okay, so it is reprogrammable, faster iteration, and a non-recurring engineering. It lowers the non-recurring engineerings and limited resources. So these are the some methodologies in the thing. So verification driven design, more modern chips require extensive verifications. So design along verifications alongside. When we are designing itself, they will start at verification, and while designing itself, we will start verification. So like simulation, assertion, test bench development, functional coverage, constraint random testing, verification consumes major efforts. Okay, so these all are something. Okay, next, it is full of theory. Okay, design for reuse pre-valid IP blocks. For example, UART, already you have developed something, you can use it for other applications like SPI. ARM cores, the ARM is an IP, intellectual property things. They are not chip vendors, they are only a design thing, and they will send it to, they will sell that, they will design and sell it to the chip vendors like memory controller, direct memory access. Those kind of things are reuse. That is the design for reuse. That is designed for reuse. So faster development, reduced bugs. You see, the Cortex M4 already they got designed. They have the IP. They will sell it to the chip vendor. They will go and reuse it for how many hardware you need. They will go and reuse. That is where the design for reuse. Okay, I told software and hardware and software co-design. No, It is common in embedded SoC. Okay, so hardware and software, it is a partition. Okay, for example, encryption. Okay, when you try to take the encryption, critical data path is in hardware. Okay, when we try to do some whenever something we are going to implement the encryption in the hardware level, the data path will be in the hardware level and the control will be in the software. So that is where the software and hardware co-design. Okay, so the software takes care of the control and the data path and everything is by the hardware. So those is called hardware and software co-design. Nowadays people, there are of having both hardware and software co-design knowledge, no, they are in demand. They all are in demand. Okay, now the benefits is optimized performance and flexibility. So now we will try to get an idea of the modern open source methodologies in the growing ecosystem. So Verilog, Yosis is a synthesis tool, OpenRoad, OpenSTA, Verilator, GTK Wave. So they all are used for education, research, and prototyping. Okay, and some things are used in industry wide because when the RISC-V has been come out, okay, they were using it. Okay, it is mainly used for education, research, and prototyping some stuffs. Then once it has been verified with this, they can go for proprietary and they can go and do the things. So the best practices what we can do is we want to use a synchronous register transfer logic and modular hierarchy, clear reset strategies, reusable blocks, version control, coding guidelines, and verification planning, and avoid the latch inference, asynchronous timing issues, poor naming, and monolithic RTL practices. Okay, so now we have seen. Okay, after this I'm going to write a program. Okay, so that is the practical we are going to get. We are going to start the Verilog from today onwards. Okay, so after this we will directly write our code. So now in the hardware evolution, we went manual design, then comes the hardware description language, synthesis, advanced verification, modern SoCs. So VHDL, Verilog, and now system Verilog. So design top down, bottom up, hierarchical, modular, RTL driven, verification driven, and reused based. So the modern will prefer top down, I told no, and hierarchical, synchronous, and strong verification, and hardware software co-designs. That is also very much important. Okay. So this is where the theory about all the things what I was trying to give you an idea. Okay. So now let me go and open. Okay, in the VHDL itself, open the terminal. Let me pull the terminal over here. Okay, let me pull the terminal. Let me go and pull the terminal here. Okay, and then I have something to do. Okay, now in this terminal, let me check how the terminal looks. Let me check. Okay, I want to maximize the terminal. I want to maximize the terminal. Okay. Okay. Hope you all are control C plus plus. Okay. So hope you are able to see the steps. Okay. That is what needed. Okay. So now in that, let me create a directory practicals. Okay, practicals, and I am moving into practicals. Okay, and I'm trying to move inside the practicals. Okay, let me try to see inside the practicals. So nothing is inside. Let me clear the window. Let me go and clear the window. Okay. So now let me create. Okay. So we are using Verilog. Okay. Let me check whether I have a Verilog hyphen version. Will it work? Oh, I want to give hyphen. Huh? Hyphen V. Okay. It is 2021 version 12. So my system is having an high Verilog. Okay. Still, today I'm not going to teach the logic, but I'm going to write the code in front of you. That is what the thing I'm going to do. A small AND gate. That's it. A small AND gate. Okay. So with the small AND gate, let me try to write a program. Okay. So before that, what I planned is, okay. Okay. So now I am going to use Verilog. Since I am using the Verilog, okay, since I am using the Verilog, I want to save the file in .v. You use whichever editor you want. I am going to use Vim editor, and I am using AND gate. I am going to just a simple AND gate, AND gate dot Verilog. V as an extension we want to go on create. Okay. Now I am not going to write any test bench or something like that. Okay. I want to create a module, a hardware, something, a module design. So you try to keep. I will teach this what is module and all later. Okay. You simply think that there is a module and I am going to give the module name as AND gate, and you have to end it with the this. Okay. Module I went and divided it. Okay. Now I want to give the input. Okay. So these are some keywords you have to understand it, but later I will teach you. I need two inputs. Okay. A comma B. I have input. Okay. And this input I want to connect it through the output. Whenever there is a change in input, I want to get the output. Okay. This is the output. So for a time being, don't try to get what are the keywords I'm trying. There is a separate session, but right now, uh, no, that one module gates YAB combinational. No, I am not going to use any test bench or something. I'm going to have a simple thing, and I want to see the output in the console. For that purpose, I am using. Yes, module is gates YAB. You can go and use that also. But I am going with a simple way. I am going it with a simple way. Okay. Next, I want to assign. Now only I am assigning. Okay. For the Y, I am assigning A and of B. A and of B. Okay. So let me have one separate thing. See, you can write the things in any different way. Okay. I'm going to do it. Since this is the design got over. Sir, what you are talking? Design got over. Huh? Yes, module, and I want to write end module. That's it. See, end module. Module, you are starting it with module, and then I want to go and end the module. That is okay. Now the thing comes is I want to see. I don't want to write any test bench for the design, hardware design separate and the testing separate. No, I want to combine it everything and do it. I want to combine it everything. I want to combine it and I want to do it everything. Okay. So let me do it. Okay, initial. Now here I am trying to, I want to see the uh, outputs. Okay, I want to see the outputs in the console, our console. Okay, I want to see the output in the console. It is like printf, it is like printf. Okay, it is like printf. So let me tell, I need uh, uh, the timings also, something I need, and the time. Okay, if you not, you can give the timing, no problem, or else you leave it time. And then let me use a. Okay, I want to print the a value also. Next I want to print the b value also. I want to go on the, everything want to be in binary, that is what it be. These things we will see it later. These what is these and everything we will see it later. For a time being, I'm going to write and I'm going to show you one program. Okay, that's it. Okay, so since I used time, I want to use this variable dollar symbol, and with this the time. Okay, there is some syntactical problem. And then I'm going to use a comma b comma and then y. Okay, this it will go and give me the output in the steps. Okay, next I want to see it through the wave, so dump file. This and all we will go and read it. For a time being, you just, okay, let me give the dump.vcd. It will dump, it will go and give a file. Using that file where we can go and view the things. Okay, once we give this, we want to give the argument. Okay, dump variable, dump variable. That is, I will tell what all these things at the later. Okay, so let me give and gate. Okay, so now let me go and test equal to 0. Then after 10 nanosecond, after 10 nanosecond, let me go on to change the output to 0 and b to 1. Then after 10 nanosecond, okay, after 10 nanosecond, let me change the value a to 1 and then b to 0. Then after 10 nanosecond, let me change a is equal to 1 and then b is equal to 1. Then after 10 nanosecond, let me finish it. Okay, let me give a finish. Let me go and do the finish. Okay, since we have been beginned, we want to go and end it. Okay, see, this is the thing, this is the module. I have a AND gate module there itself, and I started my uh, hardware verification and all those things in the same design itself. So I went and used initial begin. I am trying to monitor its output, and that module I am trying to end it. Okay, so now I got an file AND gate. Now I got an file called AND gate. Okay, now the question comes, how do I go and simulate? How do I go and what I will tell? How do I go and compile it? iverilog is the command, and gate, and let me have an output of simulation.out. Okay, so if I see that I got a simulation.out, and if I want to check if I want to check whether my design is having any flaw or something like that, let me use very later. Okay, let me go and use very later. Hyphen lint only and gate. Okay, it is telling lot of things because I went and used. So it tells we cannot use this code for hardware synthesizable. It is telling, okay, there is no timing to specify how much delay and all those things. A lot of things it is giving me an error. Okay, so let me wait for it. Okay, now let me do whatever the error it comes, let it come. See, now my purpose is I don't want to convert that into an hardware or something like that. I want to in the console output at time 0, when A is 0, B is 0 for AND gate, and when we change the input, the output is something. Output is, when we change the input, output is changed. Okay, and when this runs, you can see the dump file has been created. The dump file has been created. So using this dump file, I am able to see the, okay, I am able to see, I used it for 40 seconds. Okay, so if I click here, you see here B is 1. This is the thing. Okay, let me move it, move it, and again move it, all 1. Okay, so this is the basic thing. I didn't teach you any syntax, I didn't teach you anything but a small program, cat and gate, a small program, that's it. Okay, a small program. Yes, it is having. We cannot convert that into an the thing, sir. You have to use brackets, sir, for this. No, okay. What is for dump file? That is what I told. No, this dump file. When I try to run VVP command, it will create from the sim out. It will create a file where I can go and see the waves. That is where the dump file. Okay, sir, you have to use brackets, sir, for this module gates and everything. No need module gates because we are using end module. See, that is different. This is different. Okay, you don't confuse with the syntactical stuffs and everything. Okay, syntax is different. Now my idea is I want to write some code where it want to go on display in my console. Whether I am able to convert it into hardware or not, that is different. That is different. You leave that one. Okay. Now I want to, in one file, whether my AND logic, I am able to see the output in console and through the wave. Somehow with this something, I am able to do it. I will tell what is this. There is a separate session. I don't want to spend time now. Today, see, this is extra I am trying to give you guys. Okay. You maybe go and look into it and you will be getting it. Okay. But this is not a good practice of writing. I am giving you an example of how not to write. Okay. I am giving an example of how not to write. But this is good for the beginners. This is good for the beginners. And you don't want to confuse it with the syntax and all those things. That I will come back. Still we have now only 11th day. Still we have 19 days we have. Okay. So now from now onwards, we are going to learn only Verilog. And we are trying to use one small approaches to learn the things. Okay. So now the intention of this code is, we started, I want to get an output in the console, and manually I want to go and see, I want to create a file, and then I want to go and see it and look into it, the waveform. So that thing with this code I am able to get it. Still you can go and have see, you can go and take this out, and you can go and put it in the another way. Then something you can go and use behavioral way and combinational things. Lot and other things are there. That difference we will try to learn later. For a time being, somehow with some code I am able to get an output, and I am able to see the simulation waveform. Then slowly using this, how we can have some small modifications, then we can go and look into it. Okay, that is the idea where I went and wrote this program. Okay, so Tamana, Archana, okay, so you don't worry about the Swadi, you don't worry about these things. Okay, there is some standard, we have to go and rule it, we have to use it, I know it. But my today's intention is just to introduce one small code. That's it. Okay, don't confuse with these syntaxes and everything. Try to understand the why we need bracket, why we don't want the bracket, such kind of things. You go on, try to understand it. Why without bracket, how it is working, and all those things. You go and have it. Okay, so that is where the things for today's class. If you guys have any doubt, please let me know. Okay, don't ask these things. Simply I given you one stuff. Okay, that means you will not have doubt. Only with this we have doubt, no problem. Okay, this I have a separate thing, I will go in a separate way. Okay, that is different. Okay, just an introduced. I thought of today I want to write a code in front of you guys and go and do something. Okay, whether I am able to convert that into a synthesizable or not, that is a second story. Verification or not, that is second story. Okay, so slowly we will go and try to learn through these small codes, and we will try to understand the methodology, how we can go and do the things. Okay, so that is the idea. So I hope you guys will try this. Okay, so let me stop sharing the things. Okay, so we will see you tomorrow. Hope you guys. Okay, bye, see you tomorrow.